All right, so we looked up and I had the planetary monitor, you saw stars, right? And these stars, we realized were different brightnesses, different colors, right? And they were in groups. What were those groups? Constellations. And does every culture recognize the same groupings? Not back then. Nowadays, there's an international standard, but not then at all. Every culture had their own ones. All right. So today we're going to talk about some definitions, things that you need to know what they mean. Oh yeah, green's bad. You guys can't see green very well, can you? Can you see that? Okay. We'll switch. First of all, what is a constellation?
Grouping of stars that makes a shape, or not quite a shape, but like, I guess a reference to an animal.
Okay. Those are all right. In astronomy, we define it slightly differently. Cody? Okay. This here is a celestial sphere, a representation of the celestial sphere. Remember on Thursday, I showed you stars and I moved them, and all the sky moved together, right? So we can think of the whole sky, all the stars, as being on this perfect crystalline sphere that's rotating around the Earth, because remember, the ancient people didn't think the Earth was rotating. Doesn't feel like it's moving, so it's probably not moving. So there was this idea, what we call the celestial sphere, that all the stars are embedded on this thing, and this thing just spins around us, and it takes 24 hours to go around once. We're going to call that the celestial sphere. And all the stars are actually embedded in this celestial sphere. In fact, different cultures had different ideas what they were. Some of them thought they were like oil lamps, or they were bonfires, something that gave off light, or diamonds, or something that would shine in the night sky as it rotated around it. Okay. Well, from a scientific perspective, when we talk about a constellation, the way we define it is a group of stars which defines a location on the celestial sphere. So you kind of think of it like when you look at the world, you look at all the land split up into different countries. It's the same thing we do on the celestial sphere, as we split up the celestial sphere into different constellations, and each constellation defines a specific region on the celestial sphere. And if you're good at astronomy, you get used to knowing all the night sky, you can know exactly where all those positions are. It's very convenient. That's why you can say, oh, if somebody knows the night sky, you can say, oh, go look in the constellation of Gemini tonight for a comet. Anybody that knows where Gemini is in the world can go look at that constellation because they know where that is to define the position. Even though it's rotating around all the time, it'll be in different places for different people. If you know what that grouping of stars is, you know where to look in the sky. Okay. How many constellations are there? Give you a hint. Modern wise, we look at 88 constellations. Okay. Or we define 88 constellations that cover the whole celestial sphere. Is there anything in the night sky that is not part of the celestial sphere? The what? The moon? Okay. Is it not in the sky?
Not embedded.
on the celestial sphere.
Okay, so is the moon in a constellation?
No.
Is it in the sky?
Yes.
Do all 88 constellations cover the whole sky?
Yes.
So it has to be in a constellation.
Oh, I see what you
Yes, everything is in a constellation. Now there are things that move, right? Like the moon and the sun, and those stars are embedded. Yeah, comments, but we're not worried about them. Planets, yeah, I wanted something simple. Planets move, right? In fact, Greek, that comes from the Greek. Planet means wanderer. They wander around the celestial sphere, unlike the stars that stay in the same spot. Okay, but every one of these planets, the sun and the moon, are in different constellations. It's just their constellation changes over time. As they go around the sky, they move from constellation to another constellation. In fact, that brings us to our next definition. Zodiac constellations. What are zodiac constellations? They're defined by one object that goes through them. What is it? The sun, yes. These are the constellations the sun passes through. Each year. You're like, what? That doesn't make sense because the sun stays there. We go around the sun, right? And remember, if you're thinking about the Earth being fixed, then really what you see is the sun. And in my celestial sphere, the sun is this yellow ball right here. The sun takes 1 year to go all the way around the celestial sphere back to the same spot, the sky. And these zodiac constellations, I bet you know, because these are the ones that you use if you try to look up your horoscope. All right, ones like Leo, Cancer, Virgo. Because supposedly, on the day you were born, if the sun is in that position, that's supposedly your sign. We'll talk about, probably won't get to today, but next time, we'll talk about why that's completely wrong. It doesn't match the astronomy, but that's where it comes from. And that's where some people know those kind of constellations, is because they've heard of these because the sun passes through them. All right. Next thing we got to talk about, define, is when we go look up at the night sky, it appears like it's this half dome over your head, right? That's why we're in this room. This room with its ceiling, that's actually a half of a sphere, a hemisphere, is to mimic the night sky. And so if you're imagining you're out in the field and you're looking up at the night sky, it appears like there's a giant dome over your head. Okay. So here is our dome. Here's the ground. Here's our astronomer. We call our astronomer Herb. Why? Because I made that up 30 years ago. I have to do it every time. All right, so Herb goes out to look at the night sky. This in your way. Trying to move it out of your way, and then I made it worse. I don't know. I'm not sure which way to go. I'll put it down here. I can only move it up there when I need it. All right, and so we got to define a few things. The ground, we can't see through, right? We call this the horizon. And the horizon is imagined to be perfectly flat. Now, the reality is when you're going outside, you're looking for the stars and stuff, there's going to be buildings and trees and all the kind of stuff that gets in the way, right? But if you imagine you're out on the ocean, where the ocean is big and everything is perfectly flat, you would have a perfect horizon. It'd be a nice flat line all the way around. Okay. And on the horizon, we define what we call cardinal points. What are cardinal points? Yeah, north, south, east, and west. What defines north, south, east, and west? So, what's north mean?
Points toward in the direction of flares.
Okay, why?
Flares is the North Star and all stars revolve around.
Has it always been the North Star?
It's not. It was Newman.
Okay. What about in between those two?
There was a point in between those two stars in which everything revolved around.
That is all. All right, so how do we define north? Why do all the stars rotate around the North Star? What's spinning? Is the sky spinning? The Earth is spinning, right? Earth is a globe, right? A perfect ball. Well, it's not a perfect ball, but assume it's a perfect ball, right? It's actually not. It's bulging at the equator, but that's okay. All right, so this ball, well, if you have a ball and you want to define positions on a ball, you have to like make a reference point, right? You have to say, what's going to be our mark? And they decided, which is the most logical thing, is to use the fact that it's rotating, and so it's rotating around an axis. Right? Anything rotating has to have an axis through it. Our axis goes through the north and south poles, right? So the North Pole defines north. No matter where you're on the globe, right? You aim towards the North Pole, you're going north. You aim towards the South Pole, you're going south. So why do all the stars rotate around Polaris? Exactly. So our North Pole, if you extended this out billions and millions of miles, points close, it's not actually right, towards Polaris right now. The problem is Polaris stays in the same spot, but our axis actually changes position. But right now, it currently points close to Polaris. About like 0.6 or 7 degrees off. It's close. Just under a degree. All right. So how do we get east and west? You get north and south by the north and south poles. Where do you get east and west from? Okay, what's the equator? Okay, so if you go from the North Pole to South Pole and you cut it exactly in half, right? You get the equator, right? Where equator comes from, equal parts, right? Okay, but what's east and west? Okay, so sunrise is in the what? I ask a lot of questions, don't I? You're gonna find I'm gonna do that all semester. That's my teaching style. I ask a lot of questions. I want you to think. Okay, so which way is the Earth spinning? You're totally right, but which way? So if I look at it like this, you're looking at the Earth, right? North Pole's up. Is it spinning this way or this way? It makes that noise too. You just gotta listen really close at night. You'll hear it. This way? First one or second one? That's like the eye dot. Where's the sunrise? In the east. Why is it rising? Yes. So if it's rising, we have to be spinning toward it. Right? So if something's going to rise in the east, it's because we're spinning towards that direction. So we're actually spinning from west to east. Okay? Or if you look at it from the top down, we're going counterclockwise. Okay? Why? Which way does the moon go around the Earth? Clockwise or counterclockwise? Try again.
It goes in the same direction.
Counterclockwise. Which way does the Earth go around the sun? Clockwise or counterclockwise if north is up?
Counterclockwise.
Which way does Mars go around the sun?
Clockwise.
Which way does Mars rotate?
Counterclockwise.
Which way does Jupiter rotate?
Counterclockwise.
Which way does the sun rotate?
Clockwise.
Counterclockwise. Which way does Saturn rotate? Which way do all the planets go?
Counterclockwise except Uranus.
Yeah, well, it goes around the sun counterclockwise, but yeah, it's tilted on its side, so it's gonna mess up. But yeah, you get a hint here that everything's going counterclockwise. Mostly, there are a couple exceptions, just to mess things up. But all the major things are going counterclockwise. The reason for that is when the solar system formed, when the sun and all the planets formed, we formed out of a cloud that was spinning counterclockwise. And all that spin got transferred into the orbits of the planets and their rotation. Okay? Unless something happened to them after that point, they're still spinning that way. Okay? Venus is an exception; it's almost not spinning at all. The day on Venus is longer than the year on Venus. So we think it got hit by something really large. It was probably spinning about as fast as the Earth because it's about the same size. But then something large ran into it and it pretty much stopped its rotation. But almost all of them fit this pattern. There's a few exceptions. All right, so counterclockwise, which means we're spinning to the east, right? So the sun rises in the east. What if you live in the southern hemisphere? Does the sun still rise in the east? Anybody live in the southern hemisphere? Anybody been there? Below the equator. Just got to travel more. Does the sun rise in the east or the west?
If it did rise in the west, that would mean that the top half, the northern hemisphere would have to be spinning counterclockwise, and the southern hemisphere would be spinning clockwise.
Yeah, you guys found the big flaw in that, right? There's no way that half the Earth could spin this way and the other half could spin this way, right? It would rip the Earth apart. So of course it rises in the east, just like it rises in the east everywhere else, because the whole Earth is spinning towards the east. So everything rises in the east. Not just the sun, but all the stars, the planets, and the moon, they all rise in the east because that's the way the Earth is spinning. Okay? And yes, even in the southern hemisphere. Now there is a difference. Remember on Thursday, we had south to the front. So we're standing here. This is our Herb diagram, right? The south is to the front, north is behind you, right? Which way is east? That way or that way? East to the left or to the right? To the left. That is correct. East is over here. If we're facing south, sun rises here and goes like this, right? You with me? So if you're facing the sun is moving from left to right. Okay. You live in the southern hemisphere. The sun goes through the northern sky. So you have to turn around. East is still here. So now the sun rises in the east, but it's to the right, and it sets in the west, so it actually goes right to left. So it seems to be going backwards across the sky when you're in the southern hemisphere. It's still going east to west, but because you're on the other half of the globe, it's going right to left instead of left to right. Confusing. But if you ever get to the southern hemisphere, check it out. All right. So cardinal points. North is here. When we draw Herb diagrams, we're always going to put north on the left. Just for consistency. South is there. Which is east and which is west? The back, is that east or west? You're correct. East is there. West is here. Everybody see that? Okay. I'm actually going to draw lines through Herb to accentuate the north, south, east, west lines, right? Okay, so the cardinal points are just north, south, east, and west. And they're defined by the north and south poles. East and west are perpendicular to those poles. East is the direction the Earth is spinning. All right. Now in here, I also drew this line right here, right? This is the line that goes from the northern point of the horizon to the southern point of the horizon, but it also goes straight over Herb's head. This line is called the meridian. Don't get it confused with the prime meridian. That's a whole different thing. Okay. We'll talk about it. Meridian is the imaginary line north to south through straight overhead. What's the name of the point straight overhead? Yeah, it's called your zenith. Okay. So make sure you know meridian and zenith. We can also, let's say there's a star out here on our celestial sphere. We want to know how high that star is. We measure how far it is above the horizon as an angle. That angle we call your altitude. It's how far an object is above the horizon. All right, let's see if you understand. What's the altitude of zenith? Is it? Yes, it is, because if you move the star up to here, that would make a 90-degree angle. So yes, zenith is always going to be 90 degrees. Okay. Can you have an altitude of 120 degrees? Yeah. If you go up to 90, if you go past that, you would actually measure from the other side. You always go to the shortest distance down. So 90 is the maximum altitude. You can't have higher than 90 degrees. 90 degrees is straight up, right? So you can't go past that because then you would measure from the other side. So your altitude only goes from 0 to 90 degrees. What's the altitude of the horizon? 0 degrees. That's where you measure it from, right? This makes sense? Okay, so this is astronomy definition of altitude. All right, let me see if I covered most of the words we need here. All right, a couple more things we got to define. How do we define our position on the Earth? What coordinates? Latitude and longitude. Good. What is latitude? Of what? From where? No, but try again. Longitude is east to west. So north and south is right. I just want to know, where do you measure from? The equator. So this is how far an object is north or south of the equator. And what's your maximum value? So here's the equator. Right? And if I go up here, I'm going north, my latitude increases until I get to the North Pole, which is at 90 degrees north. And then I start going down again, right? Until I get back down to 0. So the maximum you can ever be is 90 degrees north. 90 degrees north is the North Pole. 90 degrees south is the South Pole, right? The equator has a latitude of 0. That's where we measure it from, right? So yeah, it can't be greater than 90. And with the latitude, you always have to put north or south after it. What is the latitude of Commerce, Texas? No, it's in the range. 35 is too far north. What about 33? 33.2 or something like that. If you really want to be technical, you can get it down to the nearest foot, right? Nowadays, that's how they determine where you are. That's how your phone, your watches, all that, you use GPS coordinates that put your latitude, longitude anywhere on the earth. And that's why if you get lost or something, you can tell somebody their coordinates, they can find you within like 30 feet of wherever those coordinates are. So something that could never be done before in the history of mankind, you can now do, and you walk around with it on your wrist or in your pocket. The GPS coordinates, which can also be a bad thing because if somebody can hack into it, they know exactly where you've been, right? Okay, what's longitude? Yeah.
How far east or west of you are at the line that runs through Greenwich?
Okay, what do we call that line? It's the prime meridian. So yeah, the deal is when they're, especially when they started doing all kinds of exploration in the 1600s, they were sending out ships. Europeans were sending ships all over the world, finding every places. They had to say, oh, where are we going to reference from? Where are we going to measure everything from? Okay. And every country back then actually had their own reference system. The French had their own system. There's a line drawn right through the middle of Paris. In fact, they still have markings where it is if you know where to look. London had their own, or England had their own. The Netherlands had their own. And then in the 1800s, they decided that they needed to have a universal worldwide system. And when they decided, after arguing, to use the British one. Why? It annoyed the French, of course. Well, mostly because the British were the ones to discover all these islands over here in the South Pacific, New Zealand, Australia, all these islands over here, and they were all set to London. And so it was easier to just use that because they had done the most discovery of all of them. And so they used the British system, which means they decided to set 0 as a line that goes straight from the North Pole to the South Pole, right through Greenwich, England. Now, Greenwich is just north of London. It's now actually, it's almost part of London, one of the suburbs. At the time, it was actually slightly separate. The reason it was Greenwich instead of London is that all the ships, there was a dock right there by Greenwich, and all the ship captains would, before they leave, they would have a clock. And they would set that clock to Greenwich time. It's still called Greenwich Mean Time. Nowadays, they also call it Universal Time or Zulu Time. It all means the same thing. It's the time of a clock that's set on 0. The reason that matters is your longitude, how far east or west. You're going to see exactly the same stars rise and set in exactly the same angle everywhere at the same latitude, which means right here, Kyoto, Japan is at a latitude of 33 degrees north. Hey, we're at a latitude of 33 degrees north. They see the exact same stars. They just see them 15 hours earlier than we do. So the only way you can figure out longitude is to figure out the time difference. So the ship captains would keep that clock running on London time, and then as they went around the world, they would look at the sun and figure out when noon was at that position. They compare the 2 times, and they could figure out where they were in the world. That's how you get longitude, is the difference in time. So in this class, we don't care as much about longitude, but we do care a lot about latitude. Because back the ancient people we used to talk about, they weren't discovering new places and comparing times or anything like that. All right, what, just for completeness, what's the longitude of Commerce, Texas? First, are we east or west? Longitude. West, because if you were in London, you would have to go west. Well, you wouldn't have to, but it would be wiser to go west. If you went east, you'd go a long way. How far? Nope, a good try. So here's England right here, little island up here. Here's Texas right here. About how much of a circle are we away? Oh, you're close. Yeah, 95 degrees. We're just over 90 degrees away. We're about 95 degrees west of London. So if you were in London, you went west 95 degrees, you would run into Texas. Okay. All right. So just for completeness, we're around 95 degrees west. I'm rounding that. When you get lost, don't tell them this. It's too big area. You gotta get more detail. All right. Questions about any of that? Yeah. No, it goes from 0 to 180. So you go 0 to 180 degrees east and 0 to 180 degrees west. Yeah, where's the cutoff? It's exactly half the way around the world from England, which just happens to be in the middle of the Pacific Ocean right here. In fact, they put a line right there. They call it, well, kind of right there, the international date line. Have you heard of the international date line? That's supposed to be at 180 degrees. Now, the problem is it has to wind around different island groups because you don't want different, you know, that island's on one day and the other island's on a different day. So they wind it around. So that's the case. They had to do that up here around Alaska too, because Alaska and the Aleutian Islands go way out here. So this goes here and it winds around Siberia and then it comes over here. Those weird things, but that's where it is. Yep. All right. So far, so good. Yeah. The next thing we have to talk about is angles. Don't flip the E now. We're not talking about angles. What's an angle? Yeah, well, we got to think about this, right? Let's say I see a star there and I see another star over there, and I say, hey, how far is that star to that star? And you go, well, I don't know, it's about 1.5 feet. Does that really make any sense? No. So since everything's on this sphere, right, or at least half a sphere, we have to measure everything in angles. Okay. How many degrees are there in a circle? Why? Because they told you that's what it was, right?
Full rotation.
What's that?
The full rotation.
A full rotation is 360 degrees. Yeah, but why did they pick 360? And who picked it?
That's due to the days of the year.
Days of the what?
The days of the year.
Oh, you're close, yes. The Egyptians, way back several thousand BC, were actually the first ones to come up with this idea of 360 degrees. Why? Because it's real close to 365. 365 was how long what? 365. Yeah, but they didn't think the earth was moving. It was
The
for the sun to go all the way around the celestial sphere back to its same spot. What's 365 and a quarter days, right? So we have to leap years every 4 days. Every 4 years, right? Okay, right. But why 360, not 365? They knew it was 365. You can also thank them for our clocks. Yeah. Yeah, 360 divides way more easily than 365 does, right? Okay. How many seconds in a minute? How many minutes an hour? How many hours in a day? Who invented that? The Egyptians, yeah. The Egyptians were obsessed with the number 60. We'll find different cultures have different numbers that are special to them. 60 was their special number. 365 is not divisible by 60, but 360 is, right? So that's why we have 360 degrees in a circle. It came from the Egyptians. It's also why we have 60 seconds and 60 minutes. And how long is a second?
160th.
Yeah. But how did they come up with that? They defined that. Is there something in nature that's about a second long? You all have one. Or you wouldn't be here. Your what? Your heartbeat. Yeah, resting heartbeat for an average person is around 60 beats per minute. So how many times a second? It's once, right? So it's roughly based on an average heartbeat. Okay. All right. They're also the ones that came up with the idea of AM and PM. What does AM and PM stand for? Back to my herb diagram here. This is the what? Meridian, right? We just figured that out. So AM and PM, see, you've been using this, you've been using meridian all the time, you didn't know it. AM means anti-meridian. What? Don't worry, it's Latin. And PM means post-meridian. Okay. Don't worry, you don't have to memorize these words. I just wanted to show you where they came from. Anti-meridian, anti means what? Before. Post means after. So every day, the sun rises over here in the east. It goes across the sky and it sets over here in the west. What time is it when it's exactly on the meridian? Noon, right? What we would call local noon. Doesn't match your clock, but local noon. So before that, it is anti-meridian. After that, it is post-meridian. That came from the Egyptians too. So they're the ones that came up with this idea, oh, that once you hit noon, the sun starts going down. Before it, the sun was going up. Before the meridian and after the meridian. All right. So 360 degrees in a circle. But for astronomers, a degree is too big a unit. So if I have a star here and a star here, they're 1 degree apart. We want to split that into tinier amounts. So what we do is we split 1 degree into 60 parts. And we call each of these parts an arc minute. So 60 arc minutes is equal to 1 degree. Just like 60 minutes makes an hour, right? So if I take this degree and I split it into 60 parts, each one of those parts is a arc minute. Now we usually write arc minutes as a single slash. So this symbol means arc minutes. And then we take each of these arc minutes and let's say, oh, this is still too big. We want to split that into 60 more parts. So 1 arc minute is equal to 60 arc seconds. And that's written as 2 slashes. All right. To a human, your vision is such that you can see down to about a couple arc minutes. It depends on how good your vision is, how your eyesight is. Okay, but you're without any telescope, without any aid, you can only see to a few arc minutes. About an arc minute. With the best telescopes on Earth, we can see down to about 1 arc second. We're 1/160th of an arc minute. Or how many arc seconds are in a degree? Well, there's how many arc minutes? 60, right? And there's how many seconds in each arc minute? 60. So we have 60 times 60, or 3,600 arc seconds is 1 degree. So most people think, oh, 1 degree is pretty small, right? Well, we break that in 3,600 more parts to get an arc second. That's about the limit of what you can see with a telescope from the ground, because the atmosphere gets in our way. Now, if you go into space, you can do better. That's why the Hubble Space Telescope is so good, because it could see about 100 times better than that. It was out in space, no atmosphere. The James Webb Telescope can even do better, which they just launched. All right. All this makes sense? Okay, hold your arm out like this. Thumb on the top. Okay, from the bottom of your hand to the top of your thumb is approximately 10 degrees when your arm is fully extended. Which means that, we'll test it, right? Hold it so it's exactly flat in front of you. Then don't move that, put your other hand on top of it. 20, 30, 40, 50, 60, 70, 80, and when you get to 90, it should be straight over your head. Does it? Then it's approximately 10 degrees across, right? So what's each of your fingers? Yeah, after you got 5 fingers, normal humans. Then each one's about 2 degrees, right? All right. Good. All right. One thing we have to do in this class is we have to convert DMS, means degrees, minutes, and seconds, where these are technically degrees, arc minutes, arc seconds. They just put the arc on it, okay? But we usually write this as this is the way you convert to degrees. The reason is the charts like we have in the Skywatcher's book, your book that we're going to use. Well, I'll give you something like this. It'll say, oh, the sun is at a declination, which we haven't got to yet, of 13 degrees, 24 minutes, 18 arc seconds. But if you want to put it in your calculator, you can't put it in like this. You got to put it in as a decimal degrees, like 13 point something, 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 something. So we have to be able to convert from this to this. Okay, so I'm going to show you how to convert. It's not hard. You just got to remember what the base is, right? The base is 60 between these, right? So what you do is you take the arc seconds, start here, and divide it by 60. Because we want to know how much of 60 it is. I told you you need a calculator for this class, right? Okay. So in this case, I'm going to take 18 divided by 60. Oh, and I picked one that was very simple. You get 0.3. In this case, you get 0.3. Take 18 divided by 60. Then you take that number and you add it to the minutes. This will always be a decimal, right? Because this will always be less than 60. So it's always going to be point something. And you add it to that. So then I'm going to put in here 24.3. So I added that and that together. I'm going to divide that by 60. Because there's 60 arc minutes a degree. And you get 0.405. Okay, and then you just add that to your degrees, and that's your answer. This becomes 13.0405 degrees. That is the same as that. They're just in different units. Should we do another one? Okay, do another one. Let's say we have 58 degrees, 23 minutes, 47 arc seconds. We want to convert it to degrees. What do I do first? Yeah, take the arc seconds, I divide by 60. So 47 divided by 60. And you get 0.783333. We're just going to keep it out to 3. Okay. Then what do I do with that number? Yeah, then I'm going to add it to the arc minutes. So this becomes 23.783. Divide that by 60. And I get 0.396. 396, actually, let me keep a couple more. 39638. Then what do I do with that? Add that to here, and I end up with my answer, which is 58.39638 degrees is equal to 58 degrees. Questions? It's not tricky. All we're doing is dividing by 60. Right now, we're going to make it a little trickier. Oh, good. Yeah. What if I want to go the other way? So let's say I give you a number in degrees, like 31.2574 degrees, and I want it in degrees, minutes, and seconds. Yes, we do exactly opposite. We start on the opposite side. Remember over here, we start with arc seconds. Here, we're going to start with the degrees. We know the degrees is 31, so we're going to take that off. So we got 31 degrees, and then we're going to use the 0.2574. So we just get the decimal part. And instead of dividing by 60, we're going to multiply by 60. So we're going to multiply that by 60. And you get 15.4444. Okay, and then the 15 is how many arc minutes you have. So we subtract out that part. So we got 31 degrees, 15 arc minutes. The leftover part, the 0.444. So I've just subtracted off the 15. We again multiply by 60. And you get, oh no, I need my glasses. 26.64. And that's how many arcs a second you have. So your answer is 31 degrees, 15 minutes, 26.64 arc seconds. That is equal to that number. Questions? Does this make sense? Okay. If you happen to have a calculator like this, it's actually very easy for you. They have a program in here where you can just do that. They have a button here on the side that says angles. That's second function angle. But if you go down, there's one that says DMS, and it'll take degrees, and you put in the degrees, you click on that, and it automatically converts it into this. And it can go the other way too. So if you have one like this, it's very easy to do. Not just follow the procedure. It's not hard. You just got to remember the steps. So far, so good. All right. Did everybody get a straight edge and a compass? I know everybody didn't, but most of you. If you got it, take it out. We're going to use those now. All right, we're going to learn how to do a few simple things with straight edge and compass. There's actually lots of things you can do if you're very skilled with these. But what we want to do first is we want to do something called bisect an angle. What does bisect mean? Yeah, split it exactly into two. So we have an angle, we want to split it in half. So on your paper, just arbitrarily make any angle. There's my angle. It's like a Pac-Man now. All right. Then you take your compass. Because the ancients had compasses, especially the Egyptians. They built fabulous stuff with a straight edge and a compass, right? That's a cool thing. This is how you bisect just using a compass. What you do is you open up your compass, doesn't matter how far, as long as it still is on your angle, meaning you got to be able to reach the end of it. If it goes out beyond your angle, it won't work, okay? And what you do is you set it at a certain distance. You make sure that distance doesn't change. You place the pointy end on the vertex. And you mark where those cross the angle. Essentially, you're measuring so that distance and that distance are exactly the same. You're just using your compass to make sure. Okay. Yeah, so just put the pointy thing here on the vertex and then mark on both of your lines. You could draw a whole circle if you want, it doesn't matter. But make sure you mark those 2 points. Now you can leave your compass exactly the same length. And all we're going to do is we move the point part the vertex up to the cross where it crossed here. And I'm going to draw an arc out here. The key is to make sure you don't change that distance. Don't move your compass. Then also go to the second one and draw an arc. And you see they have to cross. And as long as you didn't change that distance, that point is exactly in the middle of your angle. And then you just take your straight edge and you draw from the vertex through that line. And I split that into two perfect angles with exactly the same size in theory. And you can get really good results if you're really careful. Should I do another one? Let's do another one. What kind of angle is this? Acute. What does acute mean? That's 90 degrees. Let's see, can we do it with an obtuse angle? What does that mean? Greater than 90 degrees. Yeah. Will it work for that? Absolutely. It doesn't care. So draw a big angle. Or a bigger angle. Well, I'm going to make sure it's more than 90 degrees. What do you do first? Take your compass and yeah. We just mark it out some distance here. We just got to make sure we mark exactly the same distance on both sides. So make sure your compass stays the same distance. Oh yeah, vertex is not staying still. Hope you're doing better than I am because mine might be off a little bit. All right, then this case, I'm going to make it slightly bigger because I got to make sure it intersects in the center. Okay. All right, I'm having a compass problem. Okay. I go to the point you just made, put your point there. I draw an arc. Marker is not working well. And I go to the other one, make sure I don't change the compass. You can't change the distance. Can you mark it? And you draw a line through there. Boom. And you split that angle. Easy peasy. Okay. There's another thing we want to do with the compass. Straight edge. Oh yeah.
What do you like? What's the point of bisecting?
Yeah, we'll get to that. We'll get to that for sure. All right. Second thing we want to do is we want to be able to construct a perpendicular. make essentially exactly a 90-degree angle. In this case, you're just going to start with a line. And let's say we want a perpendicular at that point. So at this marked spot here, I want to draw a line exactly perpendicular to that line. So if you're laying out your walls of your building, your pyramid, you want that to be exactly 90-degree angle. Okay, we can do that with compass, right? In this case, you start by placing your point, funky one, at the point where you want the perpendicular to be, and you measure out an equal distance on both sides. So you hold this here, essentially you draw a mark there, flip it over and draw one on the other side. And this marker is not working. So you see I marked it here, equal distances from that one. Then we essentially do the same thing we did before. But what you do is you go out to those points you made, but you make sure that your compass is bigger than the center. It has to be a greater distance so that you mark it above and below. So you make an arc from this point greater than that distance. Don't change your distance. It's critical. Flip over and do the same thing on the other side. And you see those should intersect. Where those intersect should allow you to draw then a perfect perpendicular through that point. There's my perpendicular line. Now, if you look close, I actually missed my mark here. So I'm just going to move my mark over. That's where I wanted the perpendicular. You're really precise, you can be careful. It's hard for me to do on the blackboard. Does that make sense? Okay. Why do we do this? Well, the first thing we're going to study is to figure out where the cardinal points are, right? So if you can figure out where north is, you can figure out where south is, right? You can draw a line. East and west, you have to do a perpendicular to that to figure out exactly east and west. Questions about this? Does it seem simple? We'll find out. Because you have a homework that's due on Thursday. Yeah, go ahead.
So we're supposed to know what the degree is, right? Like not that one, but like obviously we did 90 on that one, but the first one has the other two.
Oh, no, I never gave you a measurement angle, did I? I just said split it in two. So I don't know what the angle was. I just want to see the split too. You're like, how am I going to grade it? What I grade is I look for these marks. These are called construction marks. And I can see if your arcs match up the way you're supposed to, then you did it right. That's how I judge it. All right. So here is your first homework. It is due Thursday beginning of class. All right, and let's call it a day. Remember, take your towels and throw them in the towels on the backrest. Throw them in a little bin on the way out, and I'll see you on Thursday.